What's going on, everybody? This is Mr. Diamond, and today we're going to be going over Section 3 of Chapter 1's notes. This is nuclear reactions and radiation. Now, I assume when we first started talking about radiation, especially electromagnetic radiation, something else actually popped into your head, and so we're going to talk about that stuff. While electromagnetic radiation is critical to our day-to-day life, most people are more interested in nuclear radiation or nuclear reactions. So we're going to talk about them. Now, there are two categories of nuclear reactions. The first type is fusion. Nuclear fusion is the process of making one bigger atom by taking two smaller atoms and you mush them together. They get smushed together. So in this example, we've got deuterium and tritium, and they will fuse together. So this is the blue here represents protons. So we've got one proton and a neutron, and then we've got one proton and two neutrons, and they fuse together. It's not completely stable, so after they fuse together, a neutron kind of goes flying off, but you also make a atom of helium. And so this helium is bigger than the atoms you started with, so that is a fusion process. You're fusing things together to make something bigger. The second example is fission. Fission, when I hear that, I think of fissure, which is like a crack in the ground. It's also a move in Pokemon, but that's unrelated here. It's a move in Pokemon that makes a crack in the ground, though. Fission is the opposite of fusion, and it involves the separation of one atom into two or more parts. So you're taking one big thing and you're breaking it into smaller things. So in this example, if you shoot a neutron with enough energy at certain nuclei, you'll actually split it apart and you'll get two smaller nuclei, and occasionally you'll get other neutrons out of it. This is actually the process used in the bombs that we dropped in World War II. The ones over Hiroshima and Nagasaki, they involved this fission process right here. So just a couple definitions, though, to make sure that we're kind of understanding what we're talking about here. Again, a radiation is releasing of energy in the form of electromagnetic waves or particles, and it's usually stuff that can cause ionization. So it could be electromagnetic waves, that would be electromagnetic radiation. In this case, we're talking about particle radiation or nuclear radiation. Another term that comes up a lot here is half-life. This is not the game Half-Life, those of you that are familiar with that. This is just the time it takes for a sample to be cut in half through radiation. So if you started with like 100 grams, and if the half-life was 10 minutes, or the half-life was, let's say it's half an hour. You've got 100 grams. After half an hour, radiation will have caused that 100 grams to go down to 50. And if you wait another half hour, that 50 will go to 25, and then that 25 will go to 12.5, and then from 12.5 to 6.25, and then et cetera, et cetera, et cetera. It'll keep going like that. There are three major kinds of radiation or particles: alpha, beta, and gamma. Alpha decay or alpha radiation is the emission of an alpha particle. The alpha particle contains four total particles, two protons, and two neutrons. It's represented with either an HE, but in this class we're usually going to use this. We're going to have a little alpha symbol. It's like a curvy A with a 4/2. Remember, this is just like the isotope notation that we were already doing. 4 is the mass number, 2 is the number of protons. Notice the isotope notation's coming back. You still got to be able to do that. Second type is beta decay. Beta decay is the loss of a high-energy electron. It's usually represented with a -1 on the bottom and a 0. Now, that probably seems really weird. What's really happening in the case of beta decay is that a neutron is splitting apart, and it's ejecting an electron, and that's leaving a proton behind. So the mass will stay the same. It'll lose that negative charge. That negative charge will be shooting off, but you'll increase the atomic number by 1 in that process. This will make more sense when we work out an example. Excuse me, everybody. It's early in the morning. Gamma emission is the most complicated type. We're going to work with it a little bit, but in the most part, it's actually going to be like the easiest examples to do. It involves energy being lost by changes of energy levels, not by any changes in amount of stuff in the actual atom. So we represent it with this little curvy Y shape, and it's a 0/0, which means it doesn't actually change anything. It's just energy being released, but it'll usually come with beta decay. If I don't specifically say that, though, do not just assume that there is gamma emission. Okay, there are other types of radioactive emissions other than stuff we just mentioned. We're not really going to talk about them. One example would be beta plus decay. It's the antimatter version of beta decay, so it's a positron instead of an electron. And if you're like, I only know what like half of those words mean, don't worry. This isn't going to be on the test. But its symbol would be 0 and a +1 on bottom. Another example is cluster decay, where a nucleus bigger than an alpha particle is emitted. That would be what we would call something like in this picture here, where you've got actual big chunks that are coming off of the particle that you're talking about. That'd be cluster decay. None of these are going to be on any worksheets, though. This is just to tell you an example. These are not the only ones. We're only going to focus on alpha, beta, and gamma emissions or decay. Okay, so for half-life problems, the first kind that we're going to get, this one I don't really need to click away and do a different example of. Half-life problems are really straightforward since they don't involve complex math. This is one example here. Mercury-210 has a half-life of 10 minutes. If you started with a sample of 350 grams of mercury-210 and you ended up with 10.94 grams, how much time has passed since the experiment started? I said I could work this out without writing it down, but I'm going to work this out in my example video that's going to be attached to this. I think it'll be more beneficial just so I can show you what the work should look like on a half-life problem. It's not super difficult. I'm sure a lot of you already kind of logically can figure out how to do that problem, but I'll still show you. I just want to make sure that I do it in such a way that it's a little bit more obvious what the work will look like. Solving decay problems is actually a lot easier than it may sound. Like if you heard that we are going to be learning how to solve nuclear reactions, you'd probably be like, oh god, that's going to be so much math. That's going to be so complicated. And there's versions of it that would be if you're counting the energy and things like that. But really, if we're just predicting outcomes of nuclear reactions, it's actually really easy. You're just going to follow the law of conservation of matter and make sure that all particles are accounted for. All numbers on top and bottom of each sides of your equation just need to add up to the same number. So for example, uranium-238 goes through alpha decay. What is the product? Carbon-12 goes through beta decay. What is the other product? And so again, other product would be, you know that you're going to get an alpha particle, you know that you're going to get a beta particle. So you have to just figure out the other piece. So for uranium, first you set up the equation. So we've got U-238. 238 has to go on top because it's the mass number. The bigger number goes on top. You look up uranium on the periodic table, it's got an atomic number of 92. So it's 238, 92, and then uranium. And then we're going to put an arrow. We're going to go to the other side of the equation. And then you've got to put an alpha particle because you know an alpha particle is going to be coming off of it. So an alpha particle has a mass of 4 and has 2 total protons, so it's 4, 2. Then, because I just said earlier, you have to make sure your top and your bottom numbers add up to the same thing on both sides. Since we've got 238 here, we've got 4 here, this must be added together with 4 to equal 238. So we can take 238 minus 4. Whatever is left over has to be this top piece. And then same thing down here. 92 minus 2 has to be the bottom piece. That's whatever is left over. That's what's left behind after this leaves. So when you do that math, you'll get 234 over 90. And then from here, you now know an atomic number. You have a new one, so you can go to the periodic table. You can look at 90. I'm going to look at the other side of the room. I see that 90 is thorium. Thorium is going to be the result of uranium-238 going through beta decay, and specifically it would be thorium-234. Beta decay will use the same setup. It's a little more complicated. That's the one I'm going to work out in the next example video, where I'm just kind of explaining it and working it out on paper. I believe that's all I've got for these notes, and that is actually the end of the notes for this chapter. So if you have any questions, please send me an email. Let me know. Otherwise, there is going to be examples attached to this. You can see another example being worked out if you're lost. This is the last set of notes for this chapter. We are done. If you notice, I don't have an arrow to click right here. We are out of notes. So if you have any other questions, now's the good time to ask them. The next day that we have in class, so that will be the review day, and then your test will be coming up pretty soon. So like I said, any questions, feel free to email me. Otherwise, it's Mr. Diamond signing off. Have a great rest of your day, everybody.